Today I have to cancel them, so sorry about that for anybody who was hoping to go. Yes. No, you can't do that either, actually. I'm sorry, because we have to get the new material. But Wednesday, I can answer questions, and tomorrow I'll have office hours. So sorry about that. Okay, yes. Yeah. hmm Oh, yeah. You need that. Is there a solution for it? Then use 1 times 10 to the minus third meters squared.
Number 5 is which one?
Um, okay, number 5. So I hate that name. Who thought of that name? Loaded like stress elements. Yeah, I'll write it down. But yeah, number 5. Yeah, let's say the cross-sectional area is 1 times 10 to the minus third meters squared. Um, okay, so I want to skip questions today just so we can get through enough material that you can do all the beam internal load problems. Um, so back to internal loads and beams. So far, we've done problems up to this kind of thing. Um, so let's say we have something like this with a distributed load. But what do we do when so what changes when the external loads uh, don't follow a single function over the length of the beam? Okay, so for example, let's say that uh, instead of that roller being at the end of the beam, it's at the midpoint. And that distributed load, instead of going over the entire beam, is like this. Let's say this is 1,000 newtons per meter, and each of these is 1 meter. And let's also give this a mass. Mass of the beam, let's say, is 50 kilograms. Well, for problems like the one above, we make an arbitrary cut in here, and then we calculate the internal loads for that cut as a function of x. And that gives us the function that represents each one of the internal loads. Here, like where do we make our cut? There's a qualitative difference making a cut with the right side in here versus over here. Okay, so what we're going to do is we're going to first choose the key points along the beam. Those are endpoints. Point loads. And places where distributed load functions change. Okay, so let's say that this is a total of capital N points. Once you've done that, we're going to make N minus 1 cuts. Where the left end of the chosen body, left end of chosen body is the left end of the beam. And the right end is between the key points. Okay, and we're going to calculate the internal loads on that interval. And then finally, the internal loads are going to be piecewise functions. Okay, so I think the easiest way to, so that's kind of explains how to do it generally, but I think the example will make it more clear than that will. So let's just do an example with the one that I put up here. So here's the beam. There's a roller at the center. There's a distributed load where at its maximum it has a magnitude of 1,000 newtons per meter. Each of these two lengths is 1 meter. And the mass is, what did I say, 50? And we want to calculate the distributed load, calculate the internal loads. Okay, well, the first thing we're going to have to do is calculate the external loads. And we've had ones before where we didn't have to calculate the external loads at the joints, but that was only when we had a fixed joint at the right edge, and that's because we never had a cut, or cut never represented that point, so it never showed up. If you have any joints that aren't at the far right end, then you have to do that first. Okay, now remember, the weight is a distributed load, okay? And when we do our cuts, we're going to have to think of it as a distributed load. Always before now, we've just treated the weight as a point force that acts at the center of mass, okay? But if we treated this as a beam with a force here, a weight down, and then that distributed load, our answers would be wrong, okay? We have to represent that weight force as a distributed load. But then to do the calculations of the internal loads using a distributed load, the first step is to go back to a point force, right? So it's sort of confusing, like when is it that you can represent a distributed load as a point force and when can't you? Okay, you understand the question I'm asking? Like, when is it too early to treat it as a point force? So remember, you can represent a distributed load as, I'll call it the equipolant point force. Once you've chosen the body to isolate. Okay, so if we treated that weight force as a point force right from the start, here's what would go wrong. We treat this like the weight like it was a downward force acting at the center, right? But then after we calculate the external loads, we go back in and make a cut with the right end in here somewhere, okay? And what we would have done then is represented that weight as a point force before we made this cut over here. You understand what I mean? So what we have to do instead is now once we go and make this first cut with the right end in here somewhere, we have to treat it like a distributed load. And after that, recognize that the distributed load for the weight only acts on this part now that we've chosen that little piece to isolate. And so the weight force we represent it as a point force acting at the midpoint of our cut. Okay, so that's the difference. All right, so first, external load. So free body diagram of the whole beam we'll start with. So what's acting on this? It's a pin joint at the left. So a pin joint gives you an unknown force vector. I'll call that R. And then there's a normal force at the roller. And then there are two distributed loads this time. One represents the weight. The total weight is 50 times 9.81, so 490.5. Yes. Yeah. The distributed load? Yes, I will. But this first one that I'm drawing is just the weight. Okay, so I'll have this one, and on top of it, I'll also have this one. I have to deal with both of those two individually. Okay. So for the weight force, we have a total weight of 490.5 divided by a total length of 2 meters. So 245.25, right? I know, me too. So 490.5 divided by 2 is 245.25 newtons per meter. And then this one has a maximum value of 1,000 newtons per meter. And now that we've chosen the body to isolate, we've committed ourselves to isolating the whole thing. Now we can represent it as a point force, each of those two. So I'm going to redo the free body diagram. We have the weight force, the reaction force, the normal force. The weight force acts at the middle, and the total force is the distributed load times the length of the piece that we have. So we end up with this back again, 490.5. And then the centroid of that triangular load is a third of the way from here to here, right? Or 0.6 repeating meters from the midpoint to there. And the total force is the area of that triangle. We have a height of 1,000, a base of 1. So the total area is 1,000 times 1 divided by 2. So 500. This distance here is points. It's the area of that. So the area is, base times height over 2. And the centroid of a triangle is a third of the way from the, wall side to the point side. And so now Newton's second law says Rx, Ry plus 0n plus 0 negative 490.5 plus 0 negative 500 is equal to zeros. And the moment equation, we can choose an about point. I guess I'll choose this one. So there's no moment produced by R. The 490.5, if this is the about point, the moment arm for that force is 1. And would that force produce a clockwise or counterclockwise moment around the about point? Clockwise, so it's going to be negative 1 times 490.5. And then we have the normal force. It also has a moment arm of 1. Would that produce a clockwise or counterclockwise moment? Counterclockwise, so that's going to be positive 1 times n. And then the 500, what's its moment arm? 1.6 repeating. The magnitude's 500, and is that clockwise or counterclockwise? Clockwise, so that's minus 1.6 repeating. That's 500, and that's everything, so this is equal to 0. So that is, so n is equal to 490.5 plus 833.3 repeating, I think. And what do you get if you add those up? Yeah, the 3 is repeating, yeah. Okay, and then, so we have n, and then r has a 0x component, and plug this value in for n, and what do you get for ry? $333. Okay. So here are the external loads. So this is pretty interesting. Notice for this thing to be in equilibrium, even though these two external loads, like all these are doing is making equilibrium happen with these two applied external loads, right? But in order for this to be in equilibrium, this has to pull down, okay, to counteract these two downward forces, okay? All right, are we done with this problem? No, we haven't really started it yet. All right, so now we're going to the cuts. So where do we have these key points is the question. So endpoints, first of all, there's an endpoint, there's an endpoint. And now places where you have point loads, there's one. And now places where distributed load functions change. Well, that's at the same point, so we've already chosen that point. So we're left with 3 of these key points, okay? And that means we're going to use 3 minus 1 equals 2 cuts, okay? One of those cuts is going to have the arbitrary right endpoint in between these two, and one's going to be in between these two. Well, right, because we're going to use that same idea that we did before. We're going to use an arbitrary value x. And then we'll get these functions of x, okay? And those are going to be the sub-functions that you add up to get your piecewise function. Okay, remember, so like what we're doing is, I'm going to erase this in a second, but stuff like this where you have x for x on the interval 0 to 1, or 2x squared for x between 1 and 2, or something like that. Okay, that's what we're going to do. We're just going to break up this domain x into pieces, and okay, so there are 3 key points. And those are at x equals 0, x equals 1, and x equals 2. Yes. The right end is always exclusive. The left end, since it doesn't have to do with the cuts, we're just always starting all the way from the left end, is inclusive. Okay, so we're going to do 2 cuts. The first one is for x between 0 and 1. Okay, and this is where wording-wise it gets a little confusing. Remember, I just said that the left end of the cut is inclusive. But my left boundary of the cut is exclusive. Am I stupid? Am I stupid? Okay, so when we do our when we do our cuts, the piece that we're analyzing always goes all the way from the solid left endpoint of the beam to a right endpoint that's at some value x. Okay. But when you think about what that x stands for, it stands for a range of values that are both exclusive. They're not solid. That's because when we do our cut, like when we do this cut, x always represents the right endpoint. Okay. You're always going from a solid left endpoint to some value x that's in this range. Okay. And that right endpoint, that x value is always exclusive of that point. Okay, well, maybe that'll be more clear when we do it too. So x is between 0 and 1, and then the other one is going to be x between 1 and 2. Okay, so cut 1 represents any x values between 0 and 1. Okay, so let me draw this. So the black is the piece that we're isolating. We have a downward force of 333. Was that the one? 333.3 repeating. And then we have the weight force. I'm putting it under here, but it's still just this distributed load. It has a value of 245.25 newtons per meter. This is newtons. And then there's no distributed load. I'm just going to move this so I can draw some other stuff. Okay, so this is 245.25 newtons per meter. The stuff we're not considering is the normal force at the midpoint or the distributed load from the weight over here or this distributed load. Okay. None of that is acting on our chosen piece. Are there any other loads applied to this thing? Pretty important ones. Yeah, the whole key to calculating these internal loads is that we're trying to calculate the loads applied from the missing piece to the piece that we're choosing, treating this like a fixed point. And so we also have tension, the shear force, the bending moment, and the torque. The torque is just going to be 0 in this case because I didn't apply any external torques. And now that we've chosen the body to isolate, we've committed to, let me draw this. Okay, so this distance is x. And now that we've chosen that we're going to isolate this piece that has a length of x, where x is between 0 and 1, okay, now we can represent this distributed load as a point force. Okay, so I'll redo the free body diagram. And that distributed load is a rectangular shape with a height of 245.25. And what's its width? X, yep. And so the area is the total magnitude of that force is 245.25 times x. And the centroid of a rectangle is right in the middle. Means that the distance from the end to where that point is applied is x over 2. So we have a downward force of 333.3 repeating. We have another downward force that represents the weight of 245.25x. And then we have the internal loads. There's T, V, M, some fancy T. If we would adjust at the start, so always in the past, we've just started problems by assuming the weight force is applied at the center of mass. So if we just treated this entire weight force right from the start like it acted at the center of mass of the beam, we wouldn't have this 245.25x in there, right? Because it would act over here somewhere, okay? So that's why it's important that you don't represent the distributed load as a point force until you've made your choice about what your cut is. And again, I'll choose the about point over here. I'll do that every time. So Newton's second law, we have 0, negative 333.3 repeating, plus 0, negative 245.25x, plus T0, plus 0, negative V is equal to zeros. And so that internal tension function is 0. There's no horizontal forces. But the internal shear force is negative 245.25x minus 333.3 repeating. Bless you. Okay, so in other words, that shear force starts out at, all the way at the end. There's a shear force of negative 333.3, and then it gets, I guess it gets more and more negative as you go towards the midpoint. Okay. And now the moment equation. The 333 doesn't produce a moment around that about point. The 245.25, what's its moment arm? Not quite. X over 2, yep. And does it produce a clockwise or counterclockwise rotation? Clockwise, so it's negative x over 2 times 245.25x. And then what else is going to produce a moment? We're doing this. So I'm doing this about the z-axis. I just totally skipped the moment equation about the x-axis because we don't have any external torques. But if you did that calculation, maybe we should do it in a second. We'll just see that that torque comes out to be 0. You just have fancy T is equal to 0, and so. So what else produces moments about the z-axis? The shear force does, yep. And what's its moment arm? X, yep. And clockwise or counterclockwise? Clockwise. So that's minus Vx. And anything else? One more thing. The couple, that internal couple. And so we're just adding that on as M. And now we're solving for M. So we get M is equal to Vx plus 122 point, what is it? 625 x squared. And we already calculated V. So M is equal to negative 245.2. Okay, negative 245.25 x times another x, so that's x squared, minus 333.3 repeating times x, plus 122.625 x squared. And you get a value, comes out to be negative 122.625 x squared minus 333.3 repeating x. We can do the derivative checks to make sure this works out. So remember, dm dx has to be equal to v. So you get negative 245.25x is the derivative of that, minus 333.3, and that's what you get. And the derivative of v has to be equal to the negative downward distributed load. So derivative of this with respect to x is negative 245.25. Multiplied by negative 1 gives you positive 245.25. And that's the downward distributed load. Okay, so these values, calculated these functions for t, v, and m. And those are valid only for x's on the interval from 0 to 1, not including the endpoints. Any questions about that? Yep. That's right. So now we're going to do cut 2. And this is valid for x's between 1 and 2. So now we're talking about a piece like this, leaving off some amount on the right end. We still have the downward force of 333.3 repeating. Now we have the force at the midpoint. I guess I'll put it up here just for not cluttered. What was the magnitude of that force? 1343.3 repeating. 23.83. And so now let's think about the distributed loads. There's the weight force that's represented by a there's the weight force. And we're leaving off some of it because it goes all the way to the end of the beam. And that has a magnitude of 245.25 newtons per meter. And then that triangular distributed load that goes from here to here. Does the end of that have a magnitude of 1,000 newtons per meter? We wish, yeah, because it actually continues to there, and this is where it has a magnitude of 1,000. Okay. And then what other loads are applied? Yep. The internal load, so tension, shear, bending moment, and torque. And now that we've chosen a body to isolate, we can represent these distributed loads as point forces. So let's talk about those. So start with the easy one. What's the length of this whole thing? It's x. Yep, it's x. It's just now x falls between 1 and 2 somewhere. So this has a length of x, and its height is the same all over, so 245.25. And so the area, the total force, is 245.25x. And the centroid is right in the middle again. So that's x over 2. Okay, what about the triangular load? And this one, so remember, it doesn't go all the way to x equals 0. But we're just trying to figure out the geometry of this triangle. What's the base of this triangle? Yep, perfect. S minus 1. And how are we going to represent the height of that? Well, we know it has a slope of, equal to the rise over run. So the rise is 1,000 over a run of what? 1. Yes, exactly. So we have 1,000 x. And now does it have a y-intercept? In this case, it does. You have a feel for what that would be? Yeah, it would be minus 1,000. So look, I mean, you can already see how ugly this is about to get. So the area of this triangle is 1000x minus 1000 times x minus 1. So this is, you can pull out the 1000, and that's x minus 1 times x minus 1. And so that is 1000 times x squared minus 2x plus 1. One thousand x squared minus 2000x plus 1000. Yes. Minus, this was the 1000 plus 500. Okay, and that's the magnitude of the force. Okay, that's the magnitude of a downward force, and we're going to have to represent that as a vector. So you can think of, that's the magnitude of the force. But we're going to multiply that by a unit vector that's downward. So we're going to multiply that by a vector 0, -1. Well, okay, so now redo the free body diagram. You have a downward force of 333.3 repeating. You have a weight force of 245.25x acting at the middle of this piece. The point force from the triangular distributed load is a third of the way from the midpoint to the end, or from the end to the midpoint, I guess. And it has a magnitude of 500 x squared minus 1000 x plus 500. And let's come up with a distance here. So we know that this distance is, 1/3 of the quantity x minus 1. Yep. And then we have the internal loads. Okay, so Newton's second law says 0, -333.3 repeating plus 0, -245.25x plus 0. And then here's what I was saying about this being a magnitude. This is a downward force with a magnitude that's equal to that polynomial function. So that's 0, -500x squared plus 1000x minus 500 and then plus P0 plus 0 negative V is equal to zeros. Yep. Yes. Cut 2. Oh yeah, it should be right in there. So I put in one of these, but not the other one. What was the magnitude of that? 23.83 repeating. Thanks. And that needs to fit in here somewhere too. 1323.83 repeating is equal to zeros. So we'll have to finish this next time. If any of you are interested, see if you can work through this and see if you can figure out the moment arms and stuff. But we'll go through it at the start on Wednesday. Okay, that's all.